Okay, that looks okay. All right, everyone, thanks for coming to my talk. I know it's early in the morning, so thanks a lot for being here. And thanks a lot to the organizers for inviting me. This looks like a great workshop. I'm excited to be here. So let me jump right into it. So I'm going to be telling you about a quantum linear systems algorithm with exponentially improved dependence on precision. I'm going to explain what this means in exactly one slide. And this is joint work with Andrew Childs, who you saw less than a minute ago up here, and Rolando Sama, in case you've forgotten what Andrew looks like, his picture. All right, let's start. So let me start with a one-slide summary of what this talk is going to be about, kind of like an abstract for a talk. So you know what this talk is about after this slide, and if you decide you don't care and you just want to work on your own talk, or I don't know, whatever, check Facebook or something, that's cool, or tweet about this conference, that's cool. So what we have is we know a quantum algorithm that solves, in a certain sense, which I will make very precise in the next couple of slides, a system of linear equations. And there's a little asterisk next to equations as well, because it's a certain kind of set of equations. There's some restrictions on what's allowed. And for this problem, there's a known quantum algorithm which runs in time polynomial in the log of the number of equations and the size of this matrix. So that's really nice. That's like exponentially faster than you would think is possible. And it runs in time polynomial in 1 over epsilon, where epsilon is the allowed error. And our main contribution is to bring down this error dependence from a polynomial in 1 over epsilon to logarithmic in 1 over epsilon. So that's an exponential improvement in the dependence on epsilon. Okay, this is our contribution. And in the next 40 minutes, you'll hear more about exactly what's going on. Okay, so the first part of the talk is very high level. Hopefully, should be accessible to everyone here, even if you don't do quantum algorithms. At least I'll try to make it that way. I'm going to tell you what the problem's all about, what we know about it, and what we've done. So let's get into it. So, okay, linear equations. So what is the problem of solving linear equations? You're given a system of linear equations, which I'm going to call this matrix A. It's some n by n matrix. There's some vector B. This is some vector of length n. And you want to solve the system of equations AX equals B. Okay, so the standard problem of solving a linear system of equations. Nothing fancy going on over here. And what does it mean to solve this set of equations? It means you figure out what X is. And it's OK if you figure this out approximately. That's fine if you output some approximation to X. So what is the complexity of this problem? So as stated, I haven't told you anything about how the inputs and outputs are represented. And this is always a great question to ask for any computational problem. How is the input represented? How do you want the output represented? And if you just expect the usual thing, which is the inputs are just written down for you on a piece of paper, on your Turing machine, tape, or whatever, then, well, basically classical and quantum algorithms both take polynomial time to solve this problem. There's nothing really that you can do. If everything's being explicit, you want to explicitly output a vector of length n, then, well, you're going to take n time to just write down this vector. You want to read your input, which is of size n squared. You're going to take, well, n squared time to read it. So there's really nothing that you can do with a quantum algorithm, because both classical algorithms and quantum algorithms necessarily need polynomial time in n. And classical algorithms can solve this in polynomial time in n. A common strategy for solving this is Gaussian elimination, which runs in time like roughly n cubed. You can also do a little better with fast matrix multiplication algorithms. In either case, it's important that I stress that quantum algorithms cannot give an exponential speedup for this problem, just the usual problem of solving linear systems of equations. Okay, so what am I talking about, right? So what I'm talking about is a slightly modified problem. So what do you do when there's a problem that you're not able to solve? When you hit a roadblock, you change the problem, right? That's the obvious thing to do. And so that's what we're going to do. We're going to modify the problem. And we're going to modify it in 3 ways, corresponding to the 3 variables A, X, and B. So we're going to make assumptions on the inputs, and we're going to allow a different kind of output X. So let me step through these one by one. So first, the matrix A. Right? This is the one that specifies your system of linear equations. We're going to assume it's sparse. And by sparse, what I mean is, A is a matrix of size n by n. So every row has n entries, or every column has n entries. And in principle, all n of these could be non-zero. what we're going to assume is a very stringent condition that most of these matrix entries are actually 0. And in particular, only poly log n entries per row or per column are going to be non-zero. So this is a very, strict condition on the matrix, because the matrix could have up to n non-zero entries per row or column, but we're going to say it's only a polynomial in log n. That's much smaller than potentially possible. And what we want is we want these entries to be computable efficiently. This just means that there should be some efficient algorithm, some algorithm that runs in time polynomial in log n that can tell you what the non-zero entries in every row or column are. So that's what we want for A. For the vector B, we're going to say that B is available in such a format that the quantum state corresponding to B, by which I mean just the vector B divided by the norm of the vector B, can be prepared efficiently. And by that I mean maybe there's just a quantum circuit, maybe of size poly log n, that can output this state given as input, say, the all zero state. So this is what it means for a state to be preparable efficiently. So throughout this talk, whenever I use the word efficient, this means a running time that goes like a polynomial in the log of n, not polynomial in n, because as I described in the last slide, polynomial in n is easy. You can always do this. Classical algorithms can do this. So the aim here is to be exponentially faster than classical algorithms. So that's how the input is represented. And we've also changed the goal. The goal is no longer to output the vector x. Like you no longer need to just write it all down on a piece of paper or whatever. But instead, you just need to create the quantum state corresponding to x. And again, by this I mean a quantum state whose entries are proportional to the entries of x. So it's just x divided by the norm of x. You just need to output this quantum state. And again, we allow some error. So it's OK if you output this quantum state to error epsilon. So if you output a quantum state that's epsilon close to this state in whatever your favorite norm on states is, that's fine. And this modified problem is the one that I'm going to call the quantum linear systems problem, and sometimes the QLSP. And as I said, this is different from just the usual problem of solving linear systems of equations, or the usual way in which one thinks of it. It's the same problem per se, but there's more restrictions on the input, and there's also a different way in which we want the output. So for the rest of my talk, I'm just going to be talking about this problem. So this is the quantum linear systems problem. All right, so what do we know about this problem? A couple of years ago, in 2009, Aram Harrow, Aminatan Hassidim, and Seth Lloyd showed, and two of the authors are over here, so you can talk to them if you want to, more about this result. They showed that if the matrix A is D-sparse, so D is this parameter that tells you exactly how sparse it is, so how many non-zero entries there are in every row or column. It has norm 1. This is just a condition just for concreteness. I've chosen a specific normalization. The norm of the matrix doesn't really matter because the state you're producing is, it's normalized. Has condition number kappa. So what is the condition number of a matrix? This is the ratio of the largest eigenvalue to the smallest eigenvalue. Or another way of saying it is it's just a product of the norm of the matrix and its inverse. And what does the condition number signify? It just tells you how hard it is to invert this matrix. So a matrix that's singular, so for which A inverse doesn't exist, doesn't have a well-defined condition number, or the condition number is infinite. So the larger the condition number, it tells you the harder it is to solve this inversion task. So so for a matrix that's D-sparse, has norm 1, has condition number kappa, we can solve this problem with running time that goes like, it's linear in the sparsity D, it's quadratic in this condition number kappa. It scales like 1 over epsilon in the precision, and then there's some polylog factors. So for most of the talk, I'm just going to say polylog factors, and it's not really important to worry about what the exact dependence on the smaller terms are. The important dependence is just on this polynomial dependence on D, kappa, and epsilon is what I'm going to be focusing on. And this running time that I state uses the current best algorithms for Hamiltonian simulation. And what I mean by this is their algorithm uses Hamiltonian simulation as a subroutine, but back in 2009, our Hamiltonian simulation algorithms were not as good as we have today. So the expression I've written over here uses the best known algorithms from today. So if you go back to the paper and just check the numbers are going to look different, but this is what you get if you plug in the best known stuff. So I'll be comparing with this algorithm, because otherwise it doesn't make sense to compare. And just to remind you, these are what the parameters mean. And these are the 4 parameters that are going to be important throughout this talk: n, d, kappa, and epsilon. And as I said, this algorithm uses Hamiltonian simulation. That's one of the main tools used. And the other tool used is the quantum phase estimation algorithm. And this is really going to be the source of our troubles if you try to reduce the epsilon dependence. So for those of you who are familiar with this quantum phase estimation algorithm, it's really the case that if you want to do phase estimation to differentiate between eigenvalues that are epsilon close, you have to spend resources that go like 1 over epsilon. So the main theme of this talk, we're trying to bring down the epsilon dependence from 1 over epsilon to log 1 over epsilon. This is not going to be possible if you use phase estimation as a subroutine, because phase estimation is inherently a procedure that has that kind of dependence on epsilon. So we're going to have to circumvent phase estimation. Okay. So something I didn't mention is, we changed the problem, right? So I said, let's modify the problem, let's call it this quantum linear systems problem. But now how do we know that the modified problem hasn't suddenly become trivial, hasn't just become easy for classical computers to solve? Because if that was the case, then, well, maybe there isn't so much of a point discussing quantum algorithms if there are equally good classical algorithms. And that's a very good question to ask, and this was answered in the original paper. They showed that classical algorithms cannot solve the modified problem, or, well, cannot, assuming that classical computers cannot solve, every problem that's solvable by a quantum computer. That's always, if classical computers can do that, then, well, this whole quantum algorithms thing has been a huge waste of time. But I hope that doesn't happen. And, of course, if you prove a result of this kind that classical computers cannot solve some problem that quantum computers can, it has to be modulo this assumption that there are problems that classical computers cannot solve. So, but assuming this very reasonable thing, there is no classical algorithm that solves this problem. So we're good. We're solving this problem, which is modified from the original problem, but it's an interesting problem, and also we're solving it exponentially faster than classical computers. That's right. So you have to modify it appropriately, but you can just say it's okay if you sample from the distribution that you would get if you just measured the state x in the standard basis. So even that problem is not solvable classically. So yeah, please feel free to ask questions. I don't know if I said this before, but. Right, so yeah, so we know from 2009 that we can solve this problem efficiently. And the other thing that's been done in this direction is a couple of years ago, Ambinus showed that the kappa dependence can be brought down to linear in kappa. So this algorithm has quadratic dependence in kappa. This can be brought down to linear in kappa, and this is optimal. This was also shown in the first paper that you cannot go below linear in kappa. So the best known algorithm for this currently, before our work, is linear dependence on D, linear dependence on kappa, and polynomial dependence on 1 over epsilon. So we're going to try to keep the same dependence on all the other parameters and just improve the dependence on precision. This algorithm has also found a bunch of applications, and we'll probably find more in the future. It can be used to solve differential equations on a quantum computer. It can be used for data fitting tasks, machine learning problems, etc. Some of the authors of these works are here, so if you want to know more about this, feel free to chat with them. All right, so without further ado, let's get to what we show. What we show is an improved algorithm for the exact same problem under the same constraints, the same restrictions on what kind of matrices are allowed and how the input is represented and so on. All of that stuff remains the same, and our algorithm is the running time is essentially very similar looking to theirs, except there's a 1 over epsilon factor missing. So there's no polynomial dependence on epsilon. There still is some dependence on epsilon, which is inside the polylog factors. So as I said, we bring down the epsilon dependence to polylog 1 over epsilon, but the polynomial dependence on 1 over epsilon is gone. So that's the main contribution of this work. And as I said on the previous slide, Ambinus improved the original algorithm by Harrow, Hassidim, and Lloyd to get the dependence on kappa down to linear, and we can also do the same thing. So the kappa dependence can be brought down to linear for our algorithm as well. The reason I stated separately from the main algorithm is just that this bringing down of the dependence from kappa squared to kappa has more to do with quantum algorithms magic and quantum algorithms trickery than to do with linear system solving. It's a general technique that works, and it's very technical and it's very intricate, and I won't really talk about it. I'll just try to explain the main result of how do we get the algorithm for linear system solving with polylog dependence on 1 over epsilon. And finally, you might wonder, why do we really care about this log 1 over epsilon dependence, right? Isn't 1 over epsilon good enough? And I think there's a couple of good reasons to care about this. well, other than the obvious reason, which is, well, if you can do better, well, why not do better, right? If you can achieve faster dependence, faster algorithms, then, well, why not? That's certainly a good motivation for doing something. But also, I think it's important when you're using the linear system solver as a subroutine. And what I mean by this is, say you have a quantum algorithm, and as part of the quantum algorithm, you want to solve a linear system of equations. And unless you're literally solving the problem of, a linear system of equations, you're probably going to call this algorithm a bunch of times as a subroutine, maybe with different parameters, maybe with different linear systems of equations. And what happens when you call an algorithm a whole bunch of times is that you want the algorithm to have very small error every time you call it, so that at the end of the day, the overall error of your algorithm is still small. So, for example, if you call the algorithm, I don't know, say n times, you would like that the output of the algorithm is accurate to something like 1/n precision, so that the errors that might potentially accumulate over these n calls, you're calling it n times, and all these errors might add up. You want that all these errors don't add up to so much that it completely destroys your computation. So what you would like is maybe the error to be like 1/n, and if your dependence on precision is a polynomial in 1/epsilon, then the running time of your subroutine is going to go up by a factor of the number of times you call it. So that might be, that might be bad depending on your application. If you end up calling a linear system solver a whole bunch of times, you're going to have to pay a factor proportional to how many times you call it. And that just might be too much. On the other hand, if the dependence is like log 1/epsilon, you only have to pay a log factor for the number of times you call it. So if you, call it a billion times, like the log of a billion is only, I don't know, I'll say 9 to base 10. So, you just have to pay a cost that's proportional to that. So that's nice. Of course, these constants don't actually make sense, and the log is not to base 10, but close enough. So that's one motivation, and that might be useful, especially to the applications I mentioned on the previous slide, because they use linear system solvers as a subroutine. The other motivation might just be it's kind of natural to expect log 1/epsilon scaling, and the reason is the following. When I say it as log 1/epsilon, it kind of seems it's not very clear. It doesn't seem very natural that it should be like this. But just think of the problem of, let's say, you want to compute the first k digits of the number square root of 2. Okay, let's say someone says, okay, can you print out the first k digits of square root of 2? And you think, yeah, sure, that's easy, right? You should be able to print out the first k digits of the square root of 2. But what kind of running time do you expect? Do you expect this algorithm to go like a polynomial in k? As in, can you handle k equals 100, say? Can you print out the first 100 digits of square root of 2? And you expect, yes, right? You should be able to print out the first 100 digits of square root of 2. Maybe you should even be able to print out the first, like, I don't know, 10,000 digits of the square root of 2. So you expect the running time to be proportional to the number of digits, not exponential in the number of digits. So what does it mean to print out a number to k digits of precision? It means you have the precision is actually, like the epsilon is actually 1/10 to the k. That means, the first k digits are correct. So your algorithm that runs polynomially in the number of digits of this thing, you want k digits, your algorithm's running polynomially in k, that's the same as running polynomially in log of 1/the precision. So that's why log 1/epsilon is probably pretty natural for most applications. So that's another nice reason that we would like to have log 1/epsilon dependence. All right, so that concludes the first part of my talk, which is a high-level overview of what we've done and why we should care about it and what we know about the problem. Are there any questions about this part? Just if the problem's not clear, or this would be a good time to ask questions before I start getting into technical stuff. Yeah, go ahead. Oh.
Yeah, there were optimality proofs. There was this showing that you could do a circuit by matrix inversion, and therefore there were limits on how much you can prove things just because of complexity theory. So I guess you have looked.
Right. So that's right. So that's a great question. There were a bunch of things shown to be optimal in the original paper. One of them was this thing that I said, that the kappa dependence was shown to be, you cannot go below linear. They also showed a lower bound for the dependence on 1/epsilon, but that wasn't for the problem of outputting the quantum state. It was for the problem of sampling from the quantum state, or maybe sampling with respect to some measurement that you perform with the quantum state. And once you reduce something to a sampling task, you cannot get beyond 1/epsilon dependence on the precision just for like information theoretic reasons. It has nothing to do with complexity or computation. So if you phrase your problem as just the task of, I give you a probability distribution and I tell you, well, tell me, sample, say, the first entry of the probability distribution. This is just something you cannot do unless you sample it enough. But if you phrase it as a problem of just outputting the quantum state, which might be more useful for other applications maybe, and it's a more general problem. You can always sample once you have the quantum state. You just measure it. But you could do other things, so you could use it as part of a subroutine and so on. So I think often modern treatments of this algorithm do just think of it as an algorithm for producing the quantum state. And that's the perspective we're going to take. If you really just want to sample, then there's pretty much nothing that can be done. So, right, so that answers these optimality results that were shown in the original paper. Any other questions about this? General questions about the problem or what we've done? Okay, there's another question back there.
There was the second modification that you made to simplify your problem. So I was just curious to see how this scaling works if you don't assume the second modification and do the other things.
Okay, right. So the second modification was we assume that the state B in AX equals B, the linear system of equations you're trying to solve, the state B can be prepared by an efficient quantum algorithm. If you don't make that assumption, it's not clear that any of our algorithms work, neither the original HHL algorithm nor our algorithm. And I guess in general, it's just hard. Like it's going to take, there's no way to do this in polylog n time. You're going to have to take time proportional to the size of the vector, which is n, which is exponentially larger than the times we're thinking about. And that's because, for example, what if the matrix A is just the identity matrix, and then X is just B, and now you have some B that's exponentially long and written down maybe, or even available as an oracle, but there's no way you can prepare a quantum state that's proportional to this vector in polylog time. So that assumption is crucial. All right, okay, so let me jump into some technical details. I won't get super technical about stuff, but I'll try to give you a high-level idea of what are the techniques involved in how we solve this problem. And there's essentially a main technique that I like to call the linear combination of unitaries lemma technique idea. And I'll show you how we use this technique to solve this problem. So let's just think very abstractly about a problem. The problem of implementing a map. So we're trying to implement some gate, some map V, and we don't know how to do this. We don't have an efficient quantum circuit to implement this. But what we do have is we know how to write V as a linear combination of two unitaries, U0 and U1, and these unitaries are easy to perform in the sense that there's an efficient quantum algorithm to perform these unitaries. And the question is, what can we do with this? So if the map we wanted to perform was like, let's say it was a product of unitaries, then you're in great shape, because what you do is you first apply the first unitary, then you apply the next unitary, and then, you have the unitary that you wanted to perform. Here it's a linear combination, which is kind of an unnatural thing to do with unitaries, because the linear combination of unitaries is not even necessarily unitary. So, what are you trying to do? So what we want to do is we just want to prepare a state that's proportional to V acting on the input state. V may not even be unitary, so all we need is just V acting on the input state. And so how do we do this? How do we do this from just this kind of decomposition? And there's a way to do this. It's kind of cute. It won't always give you what you want. It won't always give you V acting on the input state. But with some probability, it's going to give you V acting on the input state. So it's a probabilistic implementation of this unitary. So let's get right into it. It's pretty straightforward. The algorithm just has 3 steps. The first step is you prepare a qubit in the state square root of alpha 0 ket 0 plus square root of alpha 1 ket 1. The second register is the state on which you want to apply V. So that's just your input state ket B. That's your starting state. And on this starting state, you apply a controlled operation that reads the first qubit. And if it's a 0, it applies U0 on the second register. If it's a 1, it applies U1 on the second register. So if you do that, the state you end up with is the state written on the right. OK, that's completely straightforward. And then what you do is you measure in the basis given by square root of alpha 0, comma, square root of alpha 1, and the state orthogonal to that. So just make this measurement on the first qubit. And cross your fingers and hope that you get the first measurement outcome. Because if you get the first measurement outcome, then the state you're left behind within the second register is what we wanted. It's a state proportional to V acting on ket B. So what this is a probabilistic implementation of the state you wanted V, the map you wanted V acting on your input state B. And there's some probability of success. It might be small. And the probability is the norm of VB divided by the 1 norm of alpha, the whole squared, where the 1 norm of alpha is just the sum of alpha 0 and alpha 1. I haven't put absolute value signs around alpha 0 and alpha 1 because I've assumed them to be positive. But more generally, the 1 norm would have that. So this is a way of implementing this map that we want. And it gives it to you with some small probability. It's something. It's better than nothing, right? But this is the tool we're going to use to develop our algorithm. So this example was just with 2 unitaries. It just had 2 unitaries, U0 and U1. But more generally, if you have a linear combination of a whole bunch of unitaries, so if V is just some sum alpha I ui, then the same thing can be done. And it's essentially the same algorithm, just suitably generalized. And you can prepare the state you want, which is VB suitably normalized. And there's some small probability of this happening. And the probability is, again, the same expression as before. And this algorithm, as does the algorithm I just described, uses exactly one invocation of this controlled U operator, where the controlled U operator is this operator that looks at the first register. It reads what's there. Is it a 0 or a 1 or a 2 and so on. And based on that, it applies the appropriate unitary on the second register. So just like in this algorithm, we use the operator once. This generalization also uses the controlled operator exactly once. So what are we going to do with this, right? It doesn't seem so promising right now because there's just a low probability of success, but we're going to boost this. Okay, there's a question from Debbie. Let's go. Okay.
I suppose you do not assume the number of terms you sum over in the lemma to grow with system size? Or it will? Because then the control unitary, the complexity of it does not look obvious.
That's right, yeah. So the complexity of the controlled unitary will depend on how large, how many terms you have, like what the I is. So we're going to, I'll account for that complexity when I actually talk about my algorithm. But the lemma as stated is just, well, you need one use of the controlled unitary. But you do have to compute what this is going to cost you. And in our applications, this will actually be costly. The controlled unitary will be difficult to implement. So you have to take care of this.
The linear combination actually convex. Yeah, it's okay. Linear convex is very natural for CPTP maps. So it's a similar procedure, generalizable. Not just unitaries.
That's a good question. Yeah, I'm not completely sure about that. Yeah, I'm not sure about that. But yeah, that's a good question because for CPTP maps, linear combinations are indeed very natural, right? That's right, yeah. OK, I'll think about that. All right, so what I've shown you is a way of implementing a map that you want, that you've represented as a linear combination of unitaries, although with some small probability of success. So what are we going to do? We're going to boost this success. So this is the lemma from the previous slide. And how do you boost the success? Well, one thing you can do is just run the algorithm a whole bunch of times and just, well, hope that it works one of these times, right? That's always a viable strategy for making something work. And recall in this that if you were to use a strategy of just like trying it a whole bunch of times and hoping that one of them succeeds, you're going to have to keep making new copies of this ket B, the state that you started off with. Because when this map doesn't work, when this algorithm doesn't work, there's no guarantee on what happens with your state. So you've just lost your state, maybe. So you might just need more copies of this input state B, but that's fine, because one of the assumptions that we use in this linear system solving is that you can create this state efficiently. So that's not going to be a problem. So So yeah, how do you get from this algorithm to an algorithm that actually works with high probability? Well, A, you can just repeat it a whole bunch of times, but something a little smarter that you can do is apply amplitude amplification. This gives you a quadratic speed up over the naive algorithm of just repeating something a whole bunch of times. And what it'll give you is, under the same kind of decomposition, you've expressed a unitary as a linear combination of other unitaries. We can prepare the state corresponding to, VB with high probability this time. But we're going to make a whole bunch of uses of this unitary now. And this number of uses is going to be like inversely proportional to the probability if you did it naively just by repeating, or it's going to be inversely proportional to the square root of the probability if you use amplitude amplification. Anyway, this distinction is not super important, but you can save a quadratic factor over here. And okay, now that we have this tool, what do we do? Right? We have this tool. We want to use it to solve linear systems of equations. So what does that mean? That means we want to implement the map A inverse on the state B, right? So we want to solve AX equals B, but that's the same as X equals A inverse B. So we want to implement the map A inverse, which is not necessarily unitary. In fact, it almost certainly would not be unitary. We want to implement A inverse on the state B, and we want to implement it using this lemma. So that's our new goal. Express A inverse as a linear combination of easy unitaries. And what I mean by easy unitaries, just some unitaries for which we have efficient quantum circuits, some unitaries for which you can do this controlled operation efficiently. And just to simplify the lemma in the situation that we care about, I'm just going to get rid of the denominator in the number of uses of the controlled operator. The denominator is just the norm of this matrix acting on the vector, but since the matrix we're trying to apply is A inverse, that's just greater than or equal to 1, so it doesn't matter. So finally, we have this corollary. This is all we're going to use from the last 3 slides of discussion. The corollary is just that if you can represent the map that you want to perform, A inverse, as a linear combination of unitaries, which are easy to implement themselves, then you can prepare the state that you want it to with high probability, and your complexity is like the 1 norm of alpha times the complexity of implementing this controlled unitary operator. So this is the main corollary, and this is what we're going to use. And in the next 10 minutes or so, I'm going to try to explain to you how we represent A inverse as a linear combination of easy to implement unitaries. Okay. Any questions so far? People seem reasonably confused, not confused? Okay. It's kind of hard to tell with an audience of this size. I just hope everyone just gets it and everyone's like, yeah, this is super straightforward and very intuitive. Okay. So really the question boils down to what do we use for these unitaries, UI, right? We're trying to implement this map, A inverse, in terms of as a linear combination of UIs. So, well, the UIs need to depend on A somehow, obviously, right? Because you're not going to be able to represent A as a linear combination of stuff that has nothing to do with A. What unitaries do we know that somehow depend on a sparse n by n matrix? And if you've worked on quantum algorithms before, then you've probably seen one thing you can do is you can use Hamiltonian simulation as a subroutine. So Hamiltonian simulation is an algorithm that efficiently prepares for you a quantum circuit that applies the unitary corresponding to e to the minus iat. So A is the matrix A, t is just some time t. That's a parameter that you get to choose. And it's known from the previous work on Hamiltonian simulation that this is a unitary that we can perform efficiently for the kind of matrix A that we've assumed. We've assumed it to be sparse and representable by this kind of oracle. So if you have this kind of representation, this is something you can do. This unitary clearly depends on A. There's also a free parameter t, so that can give you many different unitaries, one for each choice of t. Potentially, and if you could represent A inverse as a linear combination of this kind, then that would be great. You'd be able to apply this corollary, and then you would get an algorithm for A inverse.
Matrix A is not this. What conditions do you put on A to make the exponential unitary?
I see. That's right. So I said the matrix is square, but I should have also said that one of the original assumptions was that the matrix is Hermitian. Yes, that's a good point. Yeah, I completely forgot to say that. But the matrix is Hermitian. This is also an assumption of the original algorithm, but it is without loss of generality in some sense. In the original algorithm, in the original paper, they show you a reduction to go from a matrix A that's not Hermitian to a matrix that is Hermitian, and essentially the reduction is just, well, you make a big block matrix, and the off-diagonal blocks are going to be A and A conjugate transpose. So, but yeah, for this talk, I'm going to assume that A is Hermitian. And once A is Hermitian, exponential of minus IAT is guaranteed to be unitary. So we're good. This is indeed a unitary. All right, so this is one choice we can make. A pretty reasonable and canonical choice that we use Hamiltonian simulation. Another thing we can do, and this is probably less obvious, is we can use this thing that comes out of a paper written by Andrew a couple of years ago. And so Andrew constructs this quantum walk where the walk operator is a unitary matrix, which is efficient to implement. And the top left block of this quantum walk is exactly the expression I've written over there. It's the nth Chebyshev polynomial of the matrix A. And this is kind of bizarre looking, but this really does just come up on its own without any kind of weird trickery. Like if you just write down the quantum walk and you analyze it, it really is implementing the nth Chebyshev polynomial, which is kind of interesting and kind of cool. So this gives us two different choices for these UIs. You can go the Hamiltonian simulation approach and use the unitaries that arise out of Hamiltonian simulation, or you can use this quantum walk approach, and then you get to use these Chebyshev polynomials. So, okay, what do we do with these things? So coming back to the question that Debbie asked is how expensive is it to implement these UIs, and how expensive is it to implement the controlled version of these UIs? If you want to do Hamiltonian simulation, well, you need to account for the cost of Hamiltonian simulation itself, right? And the cost of Hamiltonian simulation is roughly proportional to the sparsity of the matrix times the time for which you want to evolve it. So for Hamiltonian simulation, the cost is roughly like d times t. And I'm neglecting factors that are smaller than polylog factors. And if you want to do the second approach, you want to use the quantum walk, the cost of implementing the nth Chebyshev polynomial is roughly like n. So this is just what you need to keep in mind when you're designing this algorithm. So you're trying to minimize the total cost, which is the number of uses of this unitary times the cost of doing the unitary itself. So let's use Hamiltonian simulation first, and that'll give us an idea of how this would work generally. Sorry, there's a question? Yeah.
I'm intrigued by the Chebyshev polynomial. Any connection to the sign transform in this work? Because I read recently a paper about fast sign transforms, and you have this matrix B that you can diagonalize with the sign transform. It's bidiagonal, and then you can generate a very nice algebra of a small of a sparse matrices that you can diagonalize with the sign transform, precisely using Chebyshev polynomials.
I see. Yeah, I'm not sure if there's any connection, but it sounds interesting. Yeah, I don't think I have any intuition for exactly why the Chebyshev polynomials appear, other than the fact that the Chebyshev polynomials appear when you have like some kind of rotation matrix, and if you're taking higher powers of it, the entries are like sine theta becomes sine 2 theta and 3 theta and so on, and that's like the Chebyshev polynomial. That's kind of the only intuition I have for why these guys come up in the first place. So let me just explain how do you express A inverse as a linear combination of exponentials and minus IAT, and that'll kind of give you the idea of what's going on. So our goal is, express A inverse as a linear combination of e to the minus IAT. We want to minimize the product of, this is going to tell us how expensive our algorithm is going to be. But expressing A inverse as a linear combination of e to the minus IAT is kind of the same thing as expressing some scalar x inverse as a linear combination of e to the minus ixt, right? Because both sides are diagonal on the same basis. You can diagonalize both sides of the equation, and the basis that diagonalizes A, and then it's just, you're doing this individually for each eigenvalue. So let's just think of the simpler problem. You have some scalar x, and you just want to represent the function 1 over x as a linear combination of e to the minus IAT. And now if you think about this for a few minutes, you'll see, wait, this seems wrong. This shouldn't even be possible, right? This is what the function looks like. And the function blows up at the origin, right? It just tends to infinity. How can you represent a function that goes to infinity at the origin as a finite linear sum of things, each of which are very well behaved, right? This e to the minus ixt is very nicely behaved. It's between -1 and +1. There's no way you can do this. So what's going on? So what's going on is, when does x tend to 0? What does that mean? That means one of the eigenvalues of A is tending to 0. And that's exactly when the matrix is not invertible. But we made this assumption that the matrix is invertible and in fact has low condition number. So that's what tells us that this is not going to happen. None of the eigenvalues are going to run to 0. And we in fact have a lower bound on the smallest eigenvalue. And we know it cannot be smaller than 1 over kappa, because we assume the condition number is kappa. So we don't actually need to express X inverse as a linear combination of these guys that works everywhere in the domain. All we need to do is it needs to work in this domain, which is just the absolute value of X is somewhere between 1 over kappa and 1. Because that's because we've been promised that the eigenvalues lie in this range. So if we have a decomposition that works in this range, then that's good enough for us. So this gets rid of the problem of, well, the function's blowing up at the origin. But there's still the question of, well, how do you represent this as a Fourier series expansion? So, as you can see, this is just a standard Fourier series expansion problem. You have some function of X, and you want to represent it as a linear combination of e to the minus ixt's. And what we have is this kind of interesting function that it's defined in this domain, and in the middle, like between minus 1 over kappa and 1 over kappa, we kind of don't really care what the function does. It can do whatever it feels like as long as it has a nice Fourier series expansion. And so now there's some choice, like how do we fill in the middle gap? You could just define it to be 0 in the middle, but then you're going to have a discontinuous function. That's bad. You don't want to try to represent discontinuous function with Fourier series expansion. You can try some straightforward things like just a straight line that joins whatever is in the middle. These things are going to be bad because intuitively you have a nice Fourier series expansion for something that converges well if your function is smooth. So it should be continuous. It should have many, many derivatives. So what we do is we want to come up with a function that looks very much like 1 over x, but it's also smooth, and it does not blow up at the origin. So what we end up doing is, well, shown in this graph. What we do is we just multiply the function by this function in the numerator over there, which is 1 minus x squared to the 100, let's say. This 100 is going to be a parameter. But what does this do? It smooths out the function. It's what we like to call a taming function. It tames the function at the origin. Now it makes the function 0 at the origin. That's because the function in the numerator is 0 at the origin, and it goes to 0 much faster than 1 over x, or much faster than x goes to the origin. So it's really squishes down the function at the origin, makes it just 0. But in the domain that we care about, this function is going to be 1. Or we're going to choose our parameter so that this function is 1 in the domain we care about, and 0 at the origin. So then when you take the product of this function and x, and 1 over x, you get a function that's smooth, well-behaved, very similar to the function that we wanted to implement, and is nice because now it's going to have a Fourier series expansion. So that's essentially what we do. We make some choice of this smoothing function. It's not exactly the function I've shown over here, but this was just nicer to plot. But just choose some function that makes it smooth, well-behaved, and close to the function we want. And then what we end up doing is, well, we just take the Fourier transform of this function. You get some horrible-looking mess, deal with this mess, do a lot of math, and then at the end of the day, you get something like this. So I don't want to bore you with the details, but that's like don't even read that, but it's just like a proof of concept that this can be done. You can represent the function 1 over x as a finite sum over stuff, coefficients, and e to the minus ixt. And it's all very explicit over here. All the numbers are over there. And if you just compute the costs of this approach, you'll see that the thing we're trying to minimize is the one norm of this alpha that goes like kappa log kappa over epsilon, and this maximum time for which you need to run Hamiltonian simulation, which also goes for some kappa-ish time. So the overall thing goes like d kappa squared with some polylog dependence, which is what we wanted. So this is how we do it with the Fourier approach, and in my remaining minute or so, let me just give you the idea of what we do with the Chebyshev approach. It's exactly the same thing, so I won't go over the same story. What we want to do is we want to represent A inverse as a linear combination of these Chebyshev polynomials. Again, that's the same as expressing just a scalar X inverse as a linear combination of Chebyshev polynomials. And, well, what do we do? Well, let's again do the same thing of smoothing it out, because it's not going to be possible to just represent X inverse as this kind of linear combination, because the Chebyshev polynomials are also bounded between -1 and +1. And X inverse blows up at the origin. You're not going to be able to do this. So it's the same story. And again, you use some kind of smoothing function like this one. And that's going to be great. And now what we want to do is we want to represent this function 1 minus x squared to the 100 over x as a linear combination of Chebyshev polynomials. But wait, this function is already a polynomial, right? Well, it doesn't look like a polynomial because I'm dividing by x, but if you look at the numerator, there's no constant term. So it really is just a normal, legit polynomial. And the Chebyshev polynomials are polynomials. So Well, that's a good start, but they also form a basis for polynomials. So in fact, it's kind of straightforward, if rather technical, to just take any polynomial and write it as a linear combination of Chebyshev polynomials. You can always do this. It's messy and annoying, so again, I won't bore you with the details, but it can be done. And you get an expansion into Chebyshev polynomials. And it turns out that the expansion we get is, it's pretty good, but it has a whole bunch of high-order terms of Chebyshev polynomials that we don't need. So we figured out where you can truncate these and just delete a whole bunch of terms, so we don't have to spend so much time simulating this stuff. But anyway, the usual kind of stuff. You take this polynomial, work with it, try to whittle it down to exactly what you need, get rid of the extraneous details, and just like last time, you get some kind of expression, scary-looking one like this. Maybe less scary-looking than the previous one, but you get something like this. And so, yeah, we can express this as a linear combination of Chebyshev polynomials. So same high-level ideas as the previous approach with the Fourier series expansion, but the details are somewhat different. But anyway, it doesn't matter. And finally, let me just end with a comparison of these two approaches. And the main difference between these two is the first one uses Hamiltonian simulation as a black box. It can also be used for other matrices A for which you don't know how to do this. You don't have this matrix entry oracle that we assume. So we assume that you can figure out the entries of the matrix, or maybe the matrix is not sparse to start off with. So this Chebyshev approach doesn't work at all, but if you have some other way of doing Hamiltonian simulation that does not exploit the sparsity of the matrix, but you're still able to do Hamiltonian simulation, the Fourier approach still works. So if in your application you have this kind of a matrix A, you might want to use this approach. But on the downside of the Fourier approach is it's less efficient than the Chebyshev approach. I didn't get into the details of all the log factors and so on, but if you account for every last penny, so to speak, you'll see that the Fourier approach is less efficient, but maybe it doesn't really matter. And maybe the last difference between the two is maybe one of them is easier to understand than the other one. But this kind of depends on where you're coming from. I find combinatorial proofs easier to understand. So I find the Chebyshev approach easier because it's just some polynomials, you do some math, do some combinatorics, and you get the answer. The Fourier approach has some hairy details or some analysis and like some scary math that I never studied. So depending on your background, you might like one or the other. Okay, so let me end with the same slide I started with. Thanks.
Do we have any questions for Kothari? Oh.
So these are both very nice results, and I was wondering the fact that you use this auxiliary register, this thing with the alpha coefficients. Is there anything phase estimation like about that? So if you were to, in the middle of the algorithm, measure and find out which I you obtained, would you learn information about the eigenvalues? And so could you interpret this as a smarter way of doing phase estimation? Because maybe phase estimation kind of learns more than you need to, and this sort of learns only as much as you need to. Right.
I guess that's certainly part of it, that phase estimation learns just too much information. You don't need all of that. But I'm not exactly sure how to interpret what you get when you make an intermediate measurement, because it's... I guess the way I like to think about it is, one way to do this is just explicitly extract the phases and work with the phases, but all you actually were doing was implementing some kind of low-degree polynomial over the original thing. So if you doing the explicit thing is like, now you're able to implement any function you feel like, even very crazy functions, just like completely insane functions. But what you wanted to do was something pretty straightforward. It was expressible as a low-degree polynomial. So this is an approach that tells you that if you don't need all of this crazy information about the phases, you can circumvent this. But I don't think I can answer exactly what information you have lying around in the intermediate stages of the algorithm.
So there's another way of phrasing the linear solution problem, which is to have a classical output, which is v dot x, where v is some vector that's provided as with the input. But that introduces another poly 1 over epsilon error, because you have to measure and kind of approximate. So do you have any ideas for getting rid of or reducing the error there?
That might be fundamentally impossible. It's probably along the lines of these sampling problems kind of things, that if you really just want to get Like if your vector v is just like, say, the first coefficient is 1 and all the other entries are 0, you're just trying to get the first entry out. And this is going to be hard. You're probably going to have to just sample like 1 over epsilon to gather, or maybe even 1 over epsilon squared to gather enough statistics to figure out what a given entry is like. So I don't think we can do anything to speed that up, or at least our techniques don't help, but I suspect also that it's not possible. It's a question, Seth.
This is actually a super excellent result. I'm amazed by it, and but it suggests maybe as a question to people in this room. Okay, so we have this very nice algorithm for calculating Chebyshev polynomials. Let's come up with some quantum algorithms for calculating a whole bunch of other kinds of useful sets of polynomials and see what we can do with them.
Yeah, that's a great point. It would be great to increase the toolkit of things we have available. Right now we only have the Hamiltonian simulation and now this Chebyshev polynomials, but if we had more polynomials to decompose into, we could decompose more operators presumably, or do them simpler. That would certainly be a very interesting thing to do.
Let's thank Robin again for his talk.
Thanks.